So this is an overview of our statistical terminology for hypothesis tests. And before we start, let's remember that every time we take a sample, we get different results. That's our sampling variability. We also know that when we take a sample, we expect to get something, but what we actually get in our sample might not match up to what we expect. And that's always just due to chance error. Okay, so if I flip a coin, I might expect to get 5 heads, but I might actually get 4 heads just due to chance error. But if I get something like 1 head when I flip a coin 10 times, I might think that didn't seem very likely. I might start to think that the coin was not fair. Okay, so what we're trying to do is figure out how big is our chance error? Was that bigger than it should have been? Can we explain this difference just due to chance error? Or is something actually happening? Is my coin not fair? Okay. So the null hypothesis will be a statement that the difference between what we expect to observe and what we actually observe is just due to chance. We're saying it was just chance error, nothing exciting is happening. Okay. So the null hypothesis is a statement that we actually test. All of our calculations are based on the assumption that the null is true. Okay. So we assume the null is true. So assume null is true. Then we either reject or fail to reject the null. Again, all of our calculations are based on the claim that the null is true. The alternative is a statement that the actual observed difference is real or not due to chance, that there's something happening. The alternative is usually what you actually suspect is true or what you're actually trying to show. If we can reject the null hypothesis, then we conclude that the alternative hypothesis is probably true. So our null hypothesis is our status quo, or our default hypothesis. The data are collected to see whether this hypothesis, the null hypothesis, is reasonable or not. We assess the strength of the evidence against the null hypothesis, and we hope to have strong sample evidence that the null is false before we reject it. So usually we're actually hoping to reject the null because then we can say something interesting. And the null hypothesis will always be in equals, so like it will always say the average is equal to 2.5, not that the average is greater than 2.5. The null will always be in equals. And sometimes if we're comparing our data to a standard or to past data or something, that's usually the null. So the null will be that, oh, we're the same as before, or the standard is met. Our test statistic is a way to measure the difference between the data we observed and what we expected. So when we calculate the test statistic, we assume the null is true. The farther our actual observed data is from what we expected, then the more evidence we have against the null hypothesis. There are lots of different test statistics for different situations, so many different possible hypothesis tests you could use, and each one can have a different test statistic. But for our class, we just learned a few. For the tests we've been doing, we use a z-value for our test statistics. So z-test statistics use this formula. It's always going to be your observed minus your expected over your standard error. And your z-value literally tells you how many standard errors your observed value is from your expected value. The p-value is the chance of getting a sample value or a test statistic at least as weird or as extreme as the one we got if the null hypothesis were true. So extreme means far from what we'd expect if the null were true. So going back to if we flip a coin 10 times, we would expect to get about 5 heads. So something that might be extreme would be like, oh, if I got 2 heads, that would be unlikely. And if I only got 1 head, that would be even more unlikely. That would be even more extreme. The p-value is called the observed significance level, and we find the p-value as the area under the curve. So if the p-value is small, we tend to believe that the null is false. The smaller the p-value, this is something that you're going to want to memorize. The smaller the p-value, the less likely we are to believe that the null hypothesis is plausible. So the smaller the p-value, the more evidence we have against the null hypothesis, which also means then that the smaller the p-value, the more evidence we have for the alternative, which is what we were actually hoping to show. And the p-value is the chance of us getting an observed value so different from the expected value if the null hypothesis were true. Now, another thing to memorize, the p-value is not the chance that the null hypothesis is true. Students always try to simplify that because our statement seems so long, but it's always the chance of getting our sample data if the null hypothesis were true. So we can't actually tell you the chance that the null is true. We can just say, if the null is true, this is the chance of getting our sample data. And our conclusion is we reject the null hypothesis if this p-value is small. So So that's another one you want to memorize. So for a small p-value, we reject the null. So if our p-value is less than, usually we use a cutoff of 5%. So if our p-value is less than 5%, then we reject the null hypothesis. It also means we can say our results are statistically significant, and we can say that we have evidence that, and we just write the alternative hypothesis here. So if we're talking about coins, then we'd say we have evidence that our coin is not fair because that was our alternative hypothesis. If the p-value is greater than 5%, then we fail to reject the null. It is not statistically significant, and we didn't find enough evidence to say that, and then again, you would just copy the alternative hypothesis. So in your first steps, when you write the hypothesis, make sure you write them correctly, because when you get to your conclusion, you just copy the alternative hypothesis when you write your conclusion. And as a remark, if our p-value is greater than 5%, the difference we got between our observed and expected value is probably just sampling error. If the p-value is less than 5%, the difference we got is probably not due to just chance error. Something's probably wrong with our null. So we have a graphic here. And so if we were to draw it out and graph our z-value, there's this cutoff line right here. So if our p-value is greater than 5%, what the difference between our observed and expected is probably just due to chance error or our sampling error. If it's less than 5%, that's probably not sampling error. That doesn't seem very likely. I think that something is wrong with my null. Most people use 5% as a cutoff level. Some researchers, like medical journals, use a cutoff level of 1% instead. In class, we will practice using both, but really most people, most of the time, use